Okay, so now I find my son has shuffled all my slides around. So thank you very much, John, for those kind words of introduction. So this was really, I'm sure most new professors say the same thing, is this was a really difficult talk to think about. What is it actually going to talk about? And the reason for that is I've worked on a lot of really exciting projects through my career, and John's mentioned a few of them, but equally with a lot of really exciting, interesting people. And it was trying to pin down something that perhaps I could talk about, that I'd done. I thought, well, there isn't anything really, actually, because most of what I've done has been really in collaboration with a lot of people, and that's perhaps one of the themes that will come through in this talk. So when I talk about the we, it really is the collective. It's not the royal we through this. So what I'm going to talk about is a journey that I've been through in the last couple of years. So I used to think of myself as quite an orderly and tidy engineer, used to difficult but quite neat problems. Now I'm a person who actually enjoys dealing with a bit of a mess. You see, I'd reached the point in my career where I kind of thought I understood what being an engineer was all about. I had a couple of big projects under my belt by that stage, and I thought I was actually quite good at it. How wrong I could be. So I'm going to really take you through a bit of a story about how I came to embrace the mess, and perhaps the title for this talk. And it's a bit of a messy story, unfortunately, and I'm probably going to get lost at some point, so please bear with me, and I'll try not to lose you too much, and let's see how we get on. So as promised, my daughter's bedroom. So what do I mean by a mess? So this is a conversation I do actually have most days with my daughter, who certainly embraces the mess in her bedroom, and she'd be absolutely delighted if I would do the same. But that's not the sort of mess actually I'm talking about. The mess I'm talking about is the mess we find ourselves in as a society when we tackle some of these big issues: world poverty, inequality, and dare I say it, the Brexit word. And the one I want to focus on today is, I think, the biggest mess of all, which is climate change. That, I think, is the biggest challenge we face as a society, and it's the one that we're in perhaps the biggest mess over. But to understand what I mean by a mess and perhaps some of the approaches that we've been developing there, I think it's first important to start talking a little bit about complexity. Because an engineer, I quite like complexity, and we're quite good at dealing with it. But complexity and mess aren't necessarily the same things. So this is an aerial view of the particle accelerator at CERN. I've drawn a red ring round it. It straddles some national borders there, and I think that's probably the most complicated machine on the planet. And if we are alone, probably in the universe. It's one heck of a device. This is where they control it. I mean, they must have an absolute whale of a time in there with all those computers and things to play with. And this is one of the detector arrays, and actually you probably can just about see there's a couple of people actually inside the detector. And it was only recently I realised a couple of friends I knew when I was doing my PhD were actually doing the primary research that went into making these detectors. I mean, this was quite a long-term project. It's certainly very complicated, but it's also normally quite well behaved. It didn't create the black hole that we were afraid of when it was turned on. It didn't create other forms of Armageddon, and it kind of did what it was supposed to do. And that was to prove either way the existence of the Higgs boson. So Peter Higgs and his collaborator in the 1960s came up with a theory. They predicted the existence of a particle, and then on the 4th of July 2012, there was announced that they'd actually found sufficient proof of the existence of the Higgs boson. And that came out kind of as a very clear question and a very clear answer, as a number. As an energy level of a particle they detected inside the particle accelerator. But complexity comes also in many other flavours. Machines and organisations can be very complicated, and they can show remarkable degrees of order and predictability in the outcomes for a given set of circumstances. What about other situations? Can we predict the weather in a month's time? Can we predict the outcome of the general election? Can we predict what the financial markets are going to do after the general election? And if you're trying to design some form of device or machine that's going to interface with that extreme messiness that you can find in the real world, then as an engineer that can give you really quite a headache. And what do we normally do about that? Well, in those sorts of situations, we normally try and simplify things until order returns. And we actually then have a set of clear questions. And as engineers, we call that a specification. That's something we can work to and design to. Or we just run away and avoid the problem. But what if we didn't do that? What if we didn't try to simplify the question at the beginning? What if we actually worked with that messiness? Would we come up with a different set of solutions? Would we come up with different answers? And that's really what I want to explore in the rest of this talk. So what about the big mess that I'm interested? Well, I would argue this is, as I've said earlier, this is the big question of art. This is the big issue of our time. And it's a problem I've been working on probably more or less for most of my career in engineering as a technologist. Really applying the biggest technological sledgehammer I could find to address the problem. And regrettably, I also feel part of the community that's collectively failed to really tackle this issue. So despite all that technology, you can see there's the dates of the various summits and things looking at climate change, and you can see that inexorable march of atmospheric carbon emissions progressively increasing through all that time. And I found this diagram actually on the web. It's not one of my own there, and it's got a title that is "The Real Reason We Are in the Climate Mess." And I think this starts to illustrate some of the points I want to make here and others are making when we're starting to look at the climate emergency. You see, this diagram doesn't really talk about technological sledgehammers. It talks about human priorities. It talks about economics. It talks about those social interactions. Those are the things really that we're trying to look at, rather than actually those technical, logical solutions, which will be important, but aren't all part of the answer. And you can partially illustrate part of this if you look at some of the grassroots movements that are present in our time. So, you have Extinction Rebellion at the moment, and you can absolutely feel the exasperation of the young people in those organisations. We've known about this for a long time. Why isn't anything being done about it? Well, a lot is being done, but it's not being very effective. You also have another movement. You have the yellow vests. And you can see here why looking at these social issues is so important when you're addressing something like climate change. We have a pressing need to reduce our carbon emissions. A very effective way of doing that is through things like putting fuel prices up. You make your fossil fuels more expensive, it reduces demand and it incentivises moving to alternatives. But it's a blunt instrument. It'll hit the poorest in society, and the thing I really worry about with this sort of measure is you can start to lose the consensus that's building on addressing the issues around climate change. So, we can start really my own story now. So, if we can start off with why I got interested in climate change, and also I think where I perhaps first saw the glimmer of messy problems. So this is a book by James Lovelock. And I got interested in this as a teenager. So it used to be a documentary series, I think it's still on, called Horizon at the time. I used to quite enjoy watching it. And they talked about some theories by Lovelock. That's my copy. I've had it for quite some time now, 60p from a second-hand bookshop. Now, Lovelock had been working for NASA when he wrote this book. And they'd asked him, how do you detect extraterrestrial life? That's the question they'd asked him. And he kind of made his reputation developing a sense for detecting pollutants in the atmosphere. And they'd used it to actually detect ozone, the effect of CFCs on the ozone layer. And I guess what NASA thought is he'd come up with some sort of snazzy new detector that they could put on a probe and send off to Mars. But he didn't. He took a slightly different approach. Instead, he looked at how you would spot life on Earth. He looked at the impact of living things on our own planet. And he then looked at lifeless worlds like Venus, and you notice the big difference in the atmosphere. And the idea he proposed was that life on Earth, the life on the planet, has a fundamental impact on the chemical composition of your atmosphere. It actually takes you out of equilibrium. There's a lot more oxygen in our atmosphere than there should be. If over the geological time, it should have all reacted with iron and other compounds to form an atmosphere more like you see on Venus. And part of that, he proposed this idea, which he called Gaia, where there's this biosphere that wraps around the planet and interacts with the oceans, with the atmosphere, and kind of engineers to some extent the composition. I hope you can see, as a kind of a bright-eyed teenager with a bit of an interest in science, this really did catch my imagination. And there's sort of some of the ideas, some quotes from the book. Now, I reread the book a couple of months ago, and I think you might see the trigger for why a little bit later on in the talk. And there's this other quote from the book. So pollution is not, as we are often told, a product of moral turpitude. It is an inevitable consequence of life at work. Now, Lovelock's has a bit of a love-hate relationship with the Green Movement. He's an advocate of nuclear power for some very rational reasons. But to actually be saying there's nothing you can do about pollution, that was a bit of a surprise. So I want you to hold that thought, and we'll talk a little bit more about that later. So let's move on to perhaps the next chapter in the story. And I want to, something that John mentioned earlier actually, I want to talk a little bit about the work I did at Highview Power Storage. So Highview is a technological startup. They're one that makes stuff rather than stealing your data. And as part of that is I got to start to work with some people who knew quite a bit about power grids. So if we were to have a look at electrification, I mean that's probably the biggest single technological sledgehammer that's being used to tackle climate change, by taking CO2 out of the transport sector and going forward also out of the built environment as we switch from gas to electric heating. And if you map out what the system would look like, it could look something like this. And really, everything, if you start to look at this at a fundamental level, everything starts with a photon from the sun. That can be used to generate electricity in a photovoltaic cell. It'll generate a temperature difference towards wind, and we can use that to drive a turbine. Goes into a power network, and it gets distributed around the system to end users, be those businesses or people's homes. Some of those future homes might not even be connected to the grid. We might be producing the electricity off-grid, so to speak, and doing it locally. But most of the houses that will be used in the next 30, 40, 50 years are already built, they're already connected to the power network. And then largely decoupled from that, some of that solar energy will be taken by plants to create biofuels, and a small amount of the economy, so really on aviation and shipping, might be using a little bit of biofuel. So this isn't an incorrect view in my view of the energy system, but it is a little bit of a simplistic one. And there's a couple of issues with that model which I'd like to talk about. So, go back to last summer. It was, I think to remember, it was quite warm, quite pleasant, and the World Cup was on. And we did quite well, I seem to remember. So I want to take you back to the England v Colombia game. And interesting, I was watching this game on a colleague's phone who was from Germany, which was quite an experience when we got through to the penalty shootout. But anyway, I don't want to talk about the football. I want to talk about what the power grid was doing during the match. So I've got data from 2 days there, the match day and I think it was the day before, and also the output from the national wind assets. So what were all the wind farms doing together on those 2 days? So if you look at the solid red and blue lines there, that's what the demand on the network was. Blue is match day, and you can see first of all that we were using less power on match day than we were the day before. But of course the reason for that is we're all watching telly, not doing something else which consumes a lot more power. Now the other thing you can see is these spikes at half-time, full-time, and when England win. Of course that's everybody getting up from the telly, turning kettles on, turning microwaves on, whatever they do, doing stuff. And that's quite a lot of power there. So if we look when England win, there's a power surge on the network, and you might have noticed there's a big wind farm come down on the off the Brighton coast there. So that power surge is equivalent to 2.5 times the whole peak output from that wind farm in a matter of about 3 seconds. So that's quite a challenge there. And if we look at the wind output on between the 2 days, so one day the wind was blowing a bit harder than the other, and that's equivalent to 4.5 times the output of that wind farm over a 24-hour period. So not only have you got to deal with the surges on the network when there are extraordinary events like England doing quite well in a World Cup, and also the intermittency, the variation in renewable outputs that you'll naturally get between different days. So how do you go about dealing with that? Well, we deal with that at the moment, and we do that using a storage technology. It's not a battery, it's something called pumped hydro. So what we do is, there's a big power station in North Wales that does this, in the Snowdonia National Park. And what they do is we have a lake at the top of a mountain, a lake at the bottom of the mountain. You run the water from the top lake to the bottom lake, you turn a turbine, and then when you've got a surplus of energy, you pump the water back up again. So it's beautifully simple. It's an incredible machine. It's all buried inside the mountain. But there is a problem with it. It's not a problem really with the technology. The problem is we don't have enough mountains with lakes in the right places. So pretty much every possible geological location we could build a pumped hydro station has already been used. And if you think we need a lot more storage going forward, so it's not really going to be part of the solution. So another solution is we could just use a battery. So batteries store energy chemically and then you can of course recharge and discharge them as you need. And there is another solution. So something, I work in a thermofluids group, and if you've got a hot place and a cold place, you can, by flowing the thermal energy between those two sources, you can generate work, you can generate energy. Okay, so that's sort of like a thermal type of battery. So 3 possible solutions, but they all have slightly different characteristics. So if you're interested in efficiency, chemical battery wins hands down. If you're interested in cost, then the mechanical solutions come out a lot better. And kind of the question you ask there is, well, which one do you choose? And interestingly, this is what I learned when I joined Highview, is this isn't really a winner-takes-all race. There are different types of storage you need on the network. There are some storage applications where you need to balance the grid in a few seconds. So if you think about that power surge I talked about earlier, you need to put a lot of capacity on the network very quickly. You've then got the day-to-day or between the seasons variations in demand, and you need a storage device where you can store a lot of energy for a long period of time, and maybe something like a heat storage device is more appropriate. So just talk about the Highview technology and where we got to on that. So with these types of thermal batteries, the efficiency of the device is actually proportional to the temperature difference between it's the ratio, the temperature between the hot reservoir and the cold reservoir. So where we normally think about this, this is the basics behind a jet engine, an internal combustion engine, a steam engine, is you start at ambient temperature, you burn a fuel, you get something nice and hot, and you use it to generate the power that you need. Now the thing that was interesting that Highview did is they kind of flipped the problem. So they said, well, what happens if you operated between the ambient conditions and a very cold temperature? Now, of course, because we're talking about a temperature ratio, you can get the same efficiency with a much smaller temperature difference. And that actually makes the storage of that heat, that thermal energy, or coolth they call it, how do you call something cold? It's not hot, it's coolth, that's how they tend to call it. And it makes the whole thing a lot more simple. And if we see what that looks like, so the best comparator really is the big battery that Tesla have put down in Western Australia. So that's a 129 megawatt hour battery pack. That's a picture of it. You get some idea of the scale. And if we were to store that in a thermal battery, so using a tank of liquid nitrogen at nice cold temperature, then we'd need about 1,000 tons of liquid nitrogen. That picture there, that's actually the pilot plant that I was involved with at Highview. It's not actually me in the picture, that's the station manager and the plant manager there. That tank's about 60 tons, so you need about 15 of those tanks, and that will give you the equivalent amount of storage as that big battery pack. And the nice thing about those storage tanks is it's basically like a big thermos flask. So it's nice and easy to build, it's very scalable. So if you double the size of the tank, you don't double the cost, you go up about 1.5 times. And we've got some big tanks already deployed in the UK. I mean, we store natural gas in those over at Milford Haven and over at the Isle of Grain. And the 4 tanks at the Isle of Grain, using this technology, that could keep the UK power grid going for about 4 hours at peak demand in the middle of winter. So it's a seriously scalable technology for this sort of application. So if you look at where this concept came from, so it came from an absolutely brilliant engineer I'd had the pleasure of working with Peter Dearman. So it's a genuine, a real garage inventor, natural engineer, and he started playing around with liquid nitrogen and he thought, hang on a minute, that tank of liquid nitrogen, that's a battery. So how he came to that kind of revelation. I mean, you look at some of his videos on YouTube. They're quite scary what he does with a beer keg and a car, and a tank of nitrogen. Anyway, so I came involved at this point here. So they built a kind of a lab scale plant, and basically I took it from there to here. So it was at scale. I kind of left the company, but we're still very closely involved. We did some KTPs with them. They've built a kind of a full-size plant here. This is up near Manchester, quite a large device. And the really great news is actually now they've made the first commercial sale. So there's going to be, I think it's about a 50 megawatt plant going down, connected to the national grid over the next couple of years with the promise of more. And I think what's triggered that has been the big power cuts that happened last summer when realising that energy storage is really important. And it's this interesting idea, what did I learn from all of this? So first of all, batteries aren't always the answer to the question, but it sometimes does feel like that. So I have to say, when I joined the company, I thought, I don't really understand what's all this about. And the guy who convinced me actually was one of the founders, who was a guy called Toby Peters, and he's not a technologist, he's a journalist by trade. And he had a very different way of looking at the problem. So he looked at it not as a load of tech. He thought of it as the social impact, the economic impact. Those are the things that interested him. So it gave me a very different perspective on looking at this particular issue. And from that I realised, I think, retrospectively, is understanding the why is just as important as the how. So why are you doing this? Why are you putting this storage device onto the network? What is it actually trying to do, rather than being interested in all the detail, all the techie details, which we engineers often get a bit bogged down in. And finally, Highview was a very interesting company. It was a real mixture of people from different backgrounds. We had economists there, we had people from historians, we had journalists, we had engineers. We had one of my number 2 in the company had sort of grown up in the Merchant Navy. The CEO of the company had sort of spent his career building power stations. There's me, I'd kind of worked on internal combustion engines. So this real mixture of people, and that collaboration and the different views that we all had was a real revelation, actually, and I think was part of the success that the companies had. Okay, so perhaps the last chapter of this story, and perhaps in some ways perhaps one of the most interesting ones. So I'm sure you've all heard about Dieselgate and the demise of the combustion engine and other such things. And this article came out on in The Economist not too long ago, and shall we say caused a bit of some intakes of breath in our community. So kind of having worked on this technology, on diesel technology, gasoline technology for quite a few years, this was a bit of a problem. So I had some quite stark choices here on whether to kind of pack up and do something else or press on and fight my corner. And it really is, and still is difficult times. Sort of the thoughts I've had is, am I a climate denier? Am I a diesel dinosaur? Am I doing the right thing here? It's been a bit of a moral journey, to say the least. And in the middle of this, I had some sectors within the industry saying, please keep going. We really need your research. We're going to need engines for quite a long time to come. And then others saying, well, you're just delaying electrification, you're just delaying the inevitable, just shut yourself down. You're just getting in the way. We don't need these things. And that was quite difficult. Now, I have to confess that I actually was up for packing up and doing something else. I mean, I had some interesting research streams with Highview and all that sort of thing. And then that's really perhaps, I talked about collaboration. That's where a collaboration with another such a person who's thankfully here today is Professor Atkins. And he had a slightly more combative view. And actually, I think he had the moral high ground because he's an electrical engineer. So I felt quite comfortable really with that. And what we did was we felt a bit uncomfortable about this inexorable march to electrify everything. It's the answer, tell me what the question is. And what we did was we started meeting up on a regular basis on about once a fortnight on a Friday afternoon, it's diarised as playtime. And we started running a series of thought experiments. And the first thing is we tried to understand why is it we're a bit uncomfortable with batteries being the answer to everything. And really, most engineers will show a chart exactly like this, and it's all about energy density. So if you look at things like diesel, you've got about 50 megajoules per kilogram of that sort of order, ethanol, and then, batteries are kind of all batteries, that's past, present and future technologies. The energy density is just a fraction of what you can get out of a chemical carrier like a fossil fuel or a biofuel like ethanol. And you can see even I've got, wood, cow dung and sugar on there. So just hold the cow dung thought for a bit later. So what does this mean for transport? This perhaps explains why we felt a bit uncomfortable. So, I fully embrace electromobility. That's how I commute to work I've got an e-bike, and that bike has got a 400 watt-hour battery, and that can get me 3 round trips from Shoreham to Brighton, so no range anxiety there. And if you go onto eBay, I think you can get a battery pack for about £600. So that works pretty well. Now, if I'm going to head up north and go and visit my parents, and we were going to electrify the car, it's a bit too far to cycle, so I need a slightly bigger battery, and that's a projected price for about £11,000. Now, that's not the price today. That's the projected price for about 2035. All right? Okay, I mean, a bit unfair because, of course, I can fast charge at Northampton services and half the size of the battery. And it comes down to, just over £5,000. It's starting to, it looks okay. Your car's going to be a bit more expensive, but, not outrageously. So now I'm going to look at a bit of an extreme. So what if I was going to try and ship some goods from China to Europe? Then our battery comes at around 40 terawatt hours, and I've estimated about £2.7 billion for a battery to make that journey. So that battery is going to weigh more than the boat, and I don't know how much that boat costs, but it's certainly nowhere near £2.7 billion. So really this kind of articulated where we were feeling uncomfortable with this electrification of everything argument. Is there are places where electrification makes absolutely perfect sense. My e-bike, a passenger car, it's why would you not do that? But then there are areas where it didn't make any sense, in shipping, in aviation, in long distance freight transport. Maybe if you're driving in a remote area away from a ready source of power. And that got us thinking and said, okay, so that gave us some clarity on why to challenge the electrification of pretty much everything. So we went back and said, well, is an engine a potential alternative? Can you make an engine a clean alternative to compete head on with the green credentials of a battery electric solution. So what we did was we started following these thought experiments, and we did something a bit different, and we started to try and think a bit fundamentally about what's going on inside an engine. And that was where I think part of the collaboration was really good fun, because I suppose I knew a bit about thermodynamics and about combustion. It's something I'd worked on, and I had somebody perhaps more from an electrical engineering background asking some naive but absolutely insightful and fundamental questions about what is going on inside your engine. And we normally think about an equation something like this. So we have oxygen in the air, we have fossil fuel, nitrogen, which we often forget about. They react together to produce power, heat, and then the bad stuff, the greenhouse gases and the oxides of nitrogen. Now, unfortunately, when you start to look at the consequences of that equation, then we find that efficiency is a function of compression ratio. So basically, how much we squash the gas inside the engine before we add the fuel and burn it fundamentally determines the efficiency of the process. If you squash a gas, it gets hot. If you've got a lot of heat, you produce a lot of NOx. Basically, if you're above 2000 Kelvin, you're going to produce a lot of NOx. So you end up with this uncomfortable truth that with a conventional engine, high efficiency equals high NOx. And what we felt was, well, how do we break this rule? How can we break the rules and break this relationship between efficiency and NOx? Because we felt if the engine's going to have a future, you just can't produce toxic emissions. And through that fundamental series of questioning, we had it's almost become quite a famous event with some of our collaborators. We were sat over at Ricardo with a couple of combustion experts, and somebody said, "What's a flame?" And we had to run to the library to go and look it up, because we just couldn't articulate that fundamental question. And we realised a lot of this, we were sort of overcomplicating, overconstraining the problem. We were thinking about the detail that was going on there without looking at the fundamental picture. And we realised it's all really down to chemistry. So I've got a picture of two chemical reactions going on there. So on the left-hand side, that's iron and oxygen reacting quite violently. Then on the right-hand side, acting in a more sedate manner over some long periods of time. So it's basically the very, very similar same chemical reaction, but happening at a very different rate. So what if we could control that rate of reaction inside our engine? If you control the rate of reaction, we control the temperature. If we can control the temperature, we can avoid the formation of the NOx emissions. And that's where we realised that we had to fundamentally rethink the way that we designed the engine to give us the degree of control. And that's where we had kind of one of those, oh damn, it's obvious moments. Because at the same time, I think John mentioned earlier, we've been working on this split cycle engine. So this is a different type of engine cycle. What we do is we separate, we compress our air in one cylinder, then we move it over to a different cylinder where we add the fuel and we burn it. So we have a cold cylinder and a hot cylinder. And by decoupling those two processes into different places, that gives us a couple of really interesting features. First of all, you have almost complete control of the temperature. So we can now control precisely what temperature the fuel reacts at. We also decouple this relationship between compression ratio and efficiency. So we now have an engine which can run at a high efficiency and also run at very low NOx emissions. So we basically, by changing this cycle, we'd broken the rules and come up with a new paradigm. And we tested it on our engine down the lab, and that's pretty much what we found. And that's the results that we've published last year that got quite a bit of interest from a number of quarters. So what did I learn? What did I take home from this journey? So first of all, I had to go through a process of unlearning first. So I think I knew quite a bit about the internal combustion engine when we started this, and I kind of had to forget quite a lot of that, go back to some more fundamental principles. And then through the journey, the key thing was acting and finding the right question. Now, kind of most of what we've used to develop the split cycle engine was already known. It was already out in the literature. It was spotting that combination of things to bring together by asking those right questions. Normally with an internal combustion engine, you're trying to get the conditions that we achieved in the split cycle engine, but you kind of was started with you held with the baggage of it's got to be a diesel engine, it's got to be a petrol engine. What we did was we said, well, it doesn't have to be those. What happens if we could get anything we liked? And then we came up with a different solution. Then the final thing which is a bit interesting is we really struggled to articulate what we'd done. This was quite a challenge. So you could kind of show the end results, get graphs with low NOx results and things on. But the process we'd gone through was actually quite hard to explain and articulate. And we found that pictures worked a lot better than words. And that's when I think we had the next, I suppose, moment. And we started reflecting on what actually we'd done here, because I certainly got actually more excited about the process that we'd gone through rather than actually the end outcome, even though the end outcome was quite interesting. And we realised a few things there. So first of all, we were reacting in some ways to an answer to an answer that was being imposed on us. Somebody else was coming into our patch, us as propulsion engineers in transport, and they're saying that is what you're going to have to do. And I think there's a bit of a natural reaction against that. Not particularly rational, but it was still there. It was also quite clear, it wasn't very clear about what we were trying to do, what was the problem we were trying to solve. And I have to say that a potential solution from this was pack up and go home. If we find the internal combustion engine has no future, then just go off and do something else. And that really was part of the kind of the brief we were working to. And I think there was a perceived illogical thinking from all sides. We certainly felt that some people were over-pushing electrification, were acting illogically, and I'm sure they felt the same of us. And this kind of made the situation quite political. And that's when I had a bit of a moment. And one thing I forgot to mention to John, actually, I did an MBA with the Open University a couple of years ago. And I encountered some of the concepts from Peter Chetland at Lancaster University, who proposed some different ways at looking at problems. He talked about hard systems and soft system problems. So hard system problems, difficult problems, but quite easy to define the envelope. And then we talked about soft systems, and those are those kind of messy problems with lots of social, political, kind of environmental things interacting, where you're not quite sure why is this not working? We can't explain it. And there were some real parallels with the journey we'd been on and with the soft systems methodology. I think the trigger was the fact that actually we could articulate it really better in pictures. And this is an example of some of the outputs from a soft systems approach. So that's a kind of a map of the care system, which is certainly, I think, quite a mess. There's also another, it's interesting how all these events all kind of come together at the same time. So, John had initiated a kind of a look at our school strategy at about this time. And that's something I participated in. I thought was a really good idea, and sensibly we enlisted some help from the business school. And David Foster, who's here today, came and talked a bit about strategy, and he showed this idea called the curious cloud. And I remember I was sat with some colleagues there, and we were just saying, yeah, we get all of this. So here's some ideas that come out from the business world, which are articulating very clearly some of the problems and the things we're finding in our engineering world. So we got quite excited about all of this and thought, well, we've developed a whole new method of solving problems. That's it. That's my career sorted out till retirement. But actually we hadn't. We'd actually blundered into somebody else's patch. But actually, I think that was more exciting, because what it meant is we've found a whole new group of people to collaborate with in the social sciences and the business world. That's been really quite interesting in how we bring that together into a technical science. So now I want to just return to that quote I showed from Lovelock earlier on, and about his comments on pollution and morality. So I don't think Lovelock was making a provocative statement here. I think he was merely looking at pollution in a different way. And what he was saying was, he was kind of recognising that pollution is just an inevitable feature of the activity of humans and indeed, any living organism. And, he talked about the second law of thermodynamics, and he's absolutely right. The second law of thermodynamics says if you've got a system that's working, you are going to produce some waste products, kind of what entropy is all about. And he was really just recognising that feature. I've conveniently avoided one of the other problems we had with the engine until now. So we come up with a solution where we could solve the NOx emissions. But what about the greenhouse gases? If we're still tethered to a fossil fuel, then we have perhaps a low toxic emission solution, but we still have the greenhouse gas problem. So I want to just talk a little bit more about that and reflect perhaps on some of the thoughts here that Lovelock came up with. So if we look at the sort of classic model of a circular, sustainable economy, we produce stuff, we use it, we recycle it, we have a bit of raw material coming in and it just goes round and round in circles. But as one of my PhD students told me the other day, is the flaw in that is, unless you put some energy in, it's a perpetual motion machine. And if you look at what Lovelock said, there's a rise in entropy through that. What does that mean? Entropy is that difficult thing that we always struggle to explain to our students. How do you explain entropy? Well, I think the best way of describing it here is you can't fully recycle everything. So as you go around that circle, there's going to be stuff dropping out all the time. So it's not a fully sustainable circular system. And what we've been working on recently has been thinking about other things that can drop out from the sustainable economy. And it's stuff that gets forgotten about. And the sorts of things I mean here is, from sewage waste, that's inevitably going to come out as a consequence of being in existence. And that's kind of what Lovelock was saying. The simple act of cutting the grass on your lawn, how does that get recycled into this circular economy? And the reason these things are really important is, we focus on CO2 quite a lot, but it's not the only greenhouse gas. The other devil gas is methane. Now, methane is a really, really bad gas for the climate. It's 80 times worse over a short period, over a 20-year period than CO2. So you really want to keep a good focus on cutting methane emissions. And if you look at any of the predictions of where we need to go in terms of reducing greenhouse gas emissions, there's this kind of bar on the bottom that's called fugitive methane. And that's basically recognising some of the methane that's generated through human activity, and kind of also saying there's not a lot we can do about it. So it's kind of there, it's actually under accounted for quite significantly, and there isn't really a strong consensus on what you actually do about it. So what we're proposing here is, well, what if we took some of that methane and we captured it? And we recycled it, we refined it a little bit, and we upcycled it into a transport fuel. Now, this idea of upcycling, you normally see that on trendy DIY programs, don't you? But what if we did that on an industrial scale? So there's a double win here. So first of all, methane's a great transport fuel. It's not as dense as liquid fossil fuels, but it's good enough. You can get a decent range out of a truck or a ship running on methane. And if you provided a real economic incentive for capturing it, you're taking a very dangerous greenhouse gas out of the atmosphere and doing quite a significant contribution towards reducing greenhouse gas emissions. Now, I found that quite interesting, and I think so quite a few others, and that's been some of the focus of our recent work. So what that does is it gives us a slightly different view of that energy system that I talked about earlier. So I was kind of compressed a little bit over to the right-hand side. We've got the electric system, but now we can add some new pathways. So obviously we'll do the biofuels. Personally, I don't think we should do as little of that as possible, because there's lots of issues with land substitution, taking it away from natural sources and substituting for crops. That's all a bad thing. It's one of those, unforeseen consequences. But also there's waste. Old Popeye eats his spinach. It's going to produce some waste. That's going to produce some methane. At the moment, that just goes out into the atmosphere and contributes to global warming. What if we captured that and used it for something else? What about other sources like grass clippings and the such like? We collected those. I mean, think about all the football pitches in the UK, the amount of managed grassland. You know, they're cut quite regularly. My son's football pitch, not quite as often as it should be, but still, you know, at the moment we just leave that grass in the corner, it rots down, releases methane. Again, what if we captured that? And then we could use that to power those hard to electrify applications, you know, the diggers that are working remote away from, you know, they may be putting the power lines down, so there's no electricity supply for them. So how do you power them? You know, do you drive them all the way back to an electric source, maybe 50, 100 miles away? The ships going long distances and the trucks going long distances. So this situation shows it's a little bit more messy perhaps than the simple model I showed earlier. And actually it's more messy than I've shown here, because I've shown really a division between the size of the vehicle. So we have our cars where we're going to electrify, and we have the larger vehicles which we're not. And the reality is, you know, there will be cars that have to travel long distances, maybe run those on some form of fuel, and there will also be trucks and things maybe working in a city. You could electrify those. So there's a lot more grey really in that division. And really, the division you should put is between applications where you need a high energy density on board the vehicle and ones where you need a low energy density. So where are we kind of going with this? You know, we kind of have come up with I suppose I haven't invented a process of our own, we discovered somebody else's process, and how are we going to do this? So we're trialling an initiative this year, and what we're trying to do is bring students, academics, and our kind of industrial collaborators together to work on some of these kind of wicked or messy problems. And where do we see this? We're calling it the Impact Factory, and it sits between a classic centre of excellence. So some of you might have heard of the Lockheed Martin Skunk Works. If you haven't looked them up, they made what I think is the coolest plane on the planet, the SR-71 Blackbird. You know, an amazing kind of engineering centre, but working on extremely well-defined problems. So the brief was clear, the solution was highly innovative. You then have the other end of the spectrum where you have all the innovation centres. You know, these are where you see the beanbags and things, and people sat around and drinking coffee and other things. And coming up with some really revolutionary ideas, but not really targeted at a specific problem. So kind of more of your pure science, your pure innovation types of things. So nothing wrong with either of those, they're just doing different things. So what we're thinking we're trying to do with the Impact Factory is we're trying to look at some of these messy problems where, you know, there's a pressing need, we know there's something wrong, but we can't really articulate what the problem is. We can't put the design brief, we can't put a specification in there. So we have to work at a kind of a higher level and kind of embrace this messiness before we get down to looking hard at the technology. And what really excites me about this is the opportunity to bring, you know, the young, enthusiastic minds of our students together with practitioners from academia and from industry. So people without all that baggage, don't have to do all that unlearning that I had to do when we were looking at the combustion problem. And bringing those together, we think, has got a real opportunity to help everybody. And why do I think this is working? You know, frankly, it is working very well at Brighton, and it's kind of enshrined in the DNA of this university, where we talk about practical wisdom, and the ideas that I think we're doing in the Impact Factory is just really a subset of that concept. So I just kind of wanted to end my journey now, and some of you might recognise the reference, others won't. If you don't, I suggest you go and look it up because it's quite fun. I think what I've learned from this is I started off as a few years ago as I think quite an experienced and successful engineer. I was good at dealing with very, very complicated, well-defined problems, and I was quite happy with that. And the journey I've been on with some fantastic colleagues has been really starting to work in a more uncomfortable and messy environment. And I think the thing that we as engineers need to really recognise is if you start to oversimplify a complicated, messy problem, you kind of prejudge the answer, and you're going to end up in a different, quite possibly wrong place which is why I think some of the reason we've ended up with this push for electrification in appropriate applications. So really it's embrace that mess, work with colleagues in the social sciences, practitioners who are good at this sort of thing, and I think it's good fun, and you'll end up with a better technological solution, a much better sledgehammer than you would otherwise. Okay, so I think that's all I've got to say. But what I would really like to emphasise is just some of the people who are I've worked with on this journey, particularly Andy, who really was the inspiration behind the Impact Factory, and it's been quite a ride. Okay, thank you.